So this is called as electron self-energy or fermion self-energy diagram. This is called as vacuum polarization or photon self-energy diagram. This is called as vertex correction or vertex modification. So these are the lowest order radiative corrections diagrams in QED. These are the lowest order radiative correction diagrams in QED theory. Lots of people, thousands of people are working on these things, making use of them in a commercial basis, the way we do gravity theory here. So similarly, and these people sitting at LHC, theorists, they do the corresponding theory, and experimentalists, they look for all the outcomes of these things, right? So how do you construct, now from the tree level diagram, you construct the higher order diagrams which are physically meaningful. So you can construct, making use of these three fundamental radiative correction diagrams, you can construct higher order diagrams for these processes with the help of this radiative correction. So let me just demonstrate. Let me call it this, and this is number 2. So let me make a space for this. So in the electron scattering, now, so this is the tree level diagram. You can have one fermion self-energy diagram. So what you do is you insert these three diagrams according to well-defined rules of the Feynman diagrams in your lowest order tree level diagram. So for example, I could insert a fermion self-energy diagram here or here or here or here, or here, or so let me not show all 4 of them here. It's enough to show one. You can insert either here or here or here or here. You can insert them at all of them, but then this will be a very higher order diagram, because look, one E is sitting here. E is a coupling constant of the QED theory, which is a very small tiny number. So this is already a diagram, second order diagram. You have 2 vertices. You had one, in the 3 vertices there was only one vertex. So E was sitting only at one place. Now in the second order diagram, E is sitting here, E is sitting here. Now in addition, E would be sitting here and here. So this is e to the 4. You see? So you multiply 0.01 times 0.01 square. And then if you have further higher order diagrams, you have the raised to the power. So E square, e to the 4, e to the 6, e to the 8. Okay, well, so I mean they become more and more negligible as compared to this. So major contribution comes from the ground, from the lowest order diagram, then next leading order diagram, then next to leading order diagram, and so on. Now you would also have so this is also 1, 2, 3, 4. This is also e to the power 4 diagram. I could also have, now this is I have modified the vertex here, and this becomes e to the power 4 diagram, and so this is also e to the power 4 diagram. So you can collect all these diagrams. What you do is the transition amplitude of a theory is summation over n to infinity a of n lambda to the n. So lambda is the coupling coefficient which is for QED theory. Lambda equal to E for electronic charge for QED theory. Here this AN is determined by all the Feynman diagrams, all the possible Feynman diagrams for a particular process. If we want to calculate the transition amplitude for a particular process, this is the perturbation theory involving A to AN times lambda to the N. Lambda is the coupling coefficient, which is E for the QED theory. And these ANs are determined by all the diagrams. So for second order diagram, this is the only diagram, tree level diagram. But for e to the power 4, you can construct, I have written here 1, but you can write 3 more diagrams by inserting it here or here or here. Now there is only one photon propagator, you can insert it here, this one. And vertex correction you can insert either here or either. So you collect all of them and put them in the, you can construct more higher order diagrams, right? In this also nobody prevents you from putting here, then that would be e to the 6 diagram, right? And so on. One can introduce one photon self-energy diagram here, for example. So this is how you construct higher order diagrams. So higher order diagrams are constructed using the lowest order radiative correction diagrams in any theory. So this is what we are talking about, the QED theory, right? You can develop for the complex scattering in an analogous manner. You could introduce a fermion self-energy diagram here or here or here, right, on these 3 legs, or you can introduce a photon self-energy here or here, or you could introduce a vertex correction like this, and so on. So you could construct, for any given process, you can construct higher order diagrams. So you have to first know the lowest order fundamental diagrams for any theory. You see, this is what the brave souls have tried to do for gravity theory. You see? So what you do for QED theory, QCD theory, you have many more diagrams. There are 8 gluons, and electroweak theory also W plus minus G, 3 force carriers. So there is a multiplicity of all these diagrams, but younger people are more bright, like you people. They do these things on the computer and no longer in my old-fashioned method of doing things on a piece of paper. So then it becomes too clumsy to handle things. So, but anyway, this is the situation. The main point we catch, if we were interested in constructing a correct quantum field theory of gravity, we will have to first write down the fundamental vertex diagrams for the gravity theory. We will have to write down the lowest order radiative correction diagrams for the gravity theory. Then we will have to construct the higher order diagrams for the QED theory. For example, in the same diagram, one could replace this photon by a gravity. Okay, this is how you would construct. So, in the literature, you see, this means a solid line. A solid line means a fermion propagator. A wavy line means a photon propagator. And this is in general used for bosonic propagator. So, and this people use in particular for gluons. in many string theory books dealing on this topic, you might find the same one describing the same one for describing the graviton. And in some books you will find it like this. In some articles and books, some people use this, the dashed line, to denote the graviton propagator. Okay, and some people denote it by this. Okay, but the QCD people want to reserve it for the gluon propagator. Okay, so there are not too many options, but we know what we are talking about. Okay, so essentially you replace this by a and so on. Okay, so and if you because I can see my watch, today we lost some time at the beginning, so if we would like to study, let us say, electron-electron scattering via the exchange of gravitons, then we would do a similar exercise and have the graviton propagator everywhere instead of the photon. Okay, instead of the photon propagator, we would have a graviton everywhere, and then we would eventually construct a perturbation theory, calculate it term by term, and then we would like to calculate the transition amplitude for the process. What happens, except gravity theory, in all other theories you find finite results for the transition amplitude for a process, which is very logical to think, yes, why should it be not finite? But when you do this exercise for gravity theory, this transition amplitude comes out to be infinite. This is an absurd result. Okay, electron-electron scattering via the exchange of a graviton, and I get infinite value for my transition amplitude. Does it make sense? No. It's absurd. It should be finite value, non-zero finite value, but I don't get it. You see, so there were, people started realizing the difficulties, that, oh, these are the difficulties. So, because usually what you would do, you say, oh, I can construct field theory for these three things, for electrodynamics, QCD, electroweak theory, everything. Why can't I do it the same manner? This is very, the human mind thinks like that. Why can't I do it for gravity theory? Yes, I can, but then if I do that, then I end up with infinite results for the transition amplitudes for any process, and this upsets me. Oh my goodness, so what have I done? What should I do correctly? Obviously I am doing some blunder somewhere. So this logic is correct, but there is something which we still do not know. Today we have not revealed it so far. Eventually it will turn out. I think I would we should do it little more to little more extent. So if we cannot do that today, we can do it next time. But I think we should try to understand, because this is the at the crux of the renormalization theory. This is actually the theory of renormalization. Okay, so we will see that these three processes, what they do, they renormalize our theory. So let me just speak in words at the moment. What happens is the very first 8 diagrams that I had supposing it absorbs or it emits, the electron is moving. The electron is moving and it emits a photon, or it absorbs a photon. So this is an unphysical process because it cannot be seen in nature. It's a free process taking place in the nature. what we say is that this free particle, it has some mass m0, it has some charge e0, okay, and why you can't see it? Because it has not interacted with anybody. It hasn't yet said hello. As soon as it says hello to us, it's no longer an unphysical particle, it's a physical particle. The physical particle is an physically interacting particle. So it will have its charge E and mass m, which are physically observable quantities which we measure in the laboratory. But this guy, even though being an electron, its mass m0 and charge e0, they cannot be measured in the laboratory. As soon as for measuring, it has to interact with somebody. It has to say hello, I am there. So unless the guy says, oh hello, here I am, how do you know that the photon is passing by? So the things that we measure in the laboratory are physical quantities, and they are renormalized values of the masses and charges of the particles, and obviously they are finite. We even know their values so precisely. But what about E0 and M0? Actually, the E0 and M0, the non-renormalized charges and masses, are the bare charges and masses, or the charges and masses of the bare particle, a particle which has not yet interacted with anybody. So these particles, these E0 and M0, actually they involve infinities. The non-renormalized charges and masses, they involve infinities. So what happens, actually an important outcome of quantum field theory is that the strength of a force depends on the coupling constant. It depends on the distance and energy. Okay. So we say in quantum field theory that the coupling constants vary. What is the meaning of this sentence saying coupling constants vary? Means the force changes with distance and energy. And actually this is an outcome of this particular thing, that the electron, for example, this is surrounded by a cloud of vacuum fluctuations, and the contributions of the vacuum fluctuations themselves are infinite, and the charges and masses of the bare particles are themselves infinite. But the two add up in the right manner to produce finite charges and masses, which are experimentally measured in the laboratory, which are physical. If you like, maybe we can stop. My watch says 1:47, otherwise all of us would be going hungry. So just one line I would say, that if I have a let me just say here the result which we will talk about later. So here is a propagator, fermion propagator, and it goes to plus so this is the propagator of a bare fermion, and this plus this is the propagator of the physically interacting electron. And we can calculate, this would be in terms of E0 and M0, and this would be in terms of E and M. So that would give us a connection between physical E and M with the bare E and E0 and M0. Similarly, This is a photon propagator, and this goes to a photon propagator plus a vacuum photoreceptor. Similarly, this goes to this plus this. So this is the vertex of free particle, bare particles. This plus this is the vertex of the interacting particle, physically interacting particle. This plus this is the propagator of a physically interacting photon. This plus this is the propagator of a physically interacting electron. And I will just show you the results, not derive them, because each one needs a separate 1 or 2 lectures. I will just tell you the results, how they look like here. So they give a relation of E and M with E0 and M0. And this is what one would like to do for the gravity theory, if one could do. In between, so historically people have tried to do it. Let me gradually conclude. In between supergravity theories were also considered. You consider field theory, so you either like Christian Knoll gave a talk on fermion fields in the presence of curved manifold. So you put square root of minus GD4. Right? If you like, you can put in more gravity field capital R. So now one way is to supersymmetrize this theory, or consider a supersymmetric field theory and then put it in the gravitational background. But eventually these theories also did not succeed. Eventually string theory is going to be the candidate theory for quantum theory of gravity. I think let us conclude today here. So we just conclude that string theory is going to be the candidate theory for a quantum theory of gravity. I would have many more things to convince you on that, and for the day, let us stop here. Thank you all very, very much. And I think we would now go for lunch.